3,000 years ago, Persian architects solved a problem modern engineers still charge $15,000 to fix. A structural feature that cools a home by 17 degrees Fahrenheit with zero electricity, zero moving parts, zero monthly cost. The average American household spends $1,200 a year on cooling. This technology eliminates that bill permanently. It costs $200 to build. It has been proven in university studies. So why has almost no one heard of it? By the end of this video, you will know exactly how to build this yourself for under $300. No engineering degree, no special tools, just physics that worked 3,000 years ago and still works right now. The answer starts 3,000 years ago in a desert city that should not exist. In the heart of Iran's central desert, the city of Yazd faces summer temperatures that soar above 113 degrees Fahrenheit, with the mercury sometimes climbing past 122 degrees Fahrenheit. Rain is rare, and humidity lingers in the teens. Yet for centuries, homes here have stayed cool without a single watt of electricity. The answer rises above the rooftops, the Badgir, or wind catcher. These towers, built from brick or adobe, stand 5 to 12 meters tall. Each side opens to the desert air, channeling wind down into the house below. Inside, angled blades turn the flow, guiding it past shallow pools or underground water channels known as qanats. This simple geometry, paired with the steady trickle of cool water, creates a living system that draws in fresh air and drops indoor temperatures by harnessing nothing but the sun and wind. In Yazd, survival demanded invention, so builders turned the brutal climate into an advantage, using passive design to make the impossible livable. To understand how these towers work their magic, we need to look at the physics behind their cooling power. Air moves for a reason, and the physics behind solar chimneys can be boiled down to 3 simple ideas. First, the stack effect. When sunlight heats the air inside a tall shaft, that air becomes lighter and rises. As it escapes, cooler air is pulled in from below to replace it. The bigger the temperature difference and the taller the shaft, the stronger the pull. And this is described by the equation delta P is approximately rho times G times H times delta T over T naught, where delta P is the pressure difference, rho is air density, G is gravity, H is chimney height, and T naught is the reference temperature. Second, the Bernoulli principle. When wind blows across the top of a chimney, it creates a pressure difference that helps suck air up and out, adding to the natural draft. Third, the ideal gas law. As air heats up, its density drops, making it even easier for warm air to rise and cool air to flow in. These 3 forces combine to create a measurable, predictable system. With these principles in mind, the performance claims of solar chimneys become something you can judge for yourself, using numbers, not just promises. Next, we will see how these equations play out in real-world data. Peer-reviewed measurement leaves little room for doubt. In Yazd, a modern IoT sensor campaign tracked temperature, humidity, and airflow in working Badgirs across multiple summers. The data show up to 11 complete air changes per hour, far beyond the 0.5 air changes per hour of a sealed modern house with no ventilation. During peak heat, the sensors recorded an 8 to 10 degrees Celsius drop between the outside air and the air delivered indoors. These numbers are not outliers. Computational models from the University of Nottingham and field data from the Torrent Research Center in Ahmedabad confirm that well-designed passive chimneys can cut cooling energy by 25 to 70%, with indoor temperatures consistently below outdoor peaks. The evidence is now archived and openly available, not just in Yazd, but in academic datasets worldwide. With hard numbers in hand, the question isn't whether solar chimneys work. It's why, despite proven performance, so few American homes use them. That puzzle starts with the rules that shape what gets built. Permits for new homes in the United States almost always require a mechanical ventilation system, even when passive options can deliver equal or better airflow. The International Residential Code sets mechanical ventilation as the standard, and most inspectors expect to see a powered fan or a certified HVAC unit on the plans. Developers facing tight budgets and the risk of inspection delays rarely choose unproven paths. Even if a solar chimney can meet or exceed the airflow rates in the code, there is no clear way to certify it as a substitute. The rules do not ban passive systems outright. but they do not recognize them as a primary solution either. This regulatory gap means that passive cooling is left to the margins, an accessory, not a main feature. For homeowners, this leaves one practical route. Take initiative, navigate the permit process, and build a system that works, even if it sits outside the official playbook. The next step is to see how DIY builders have started to bridge that gap. Cooling a home with a solar chimney is not just a comfort upgrade, it is a measurable shift in both carbon footprint and long-term cost. Every kilowatt hour of electricity saved by avoiding air conditioning means about 0.45 kilograms less carbon dioxide released into the atmosphere, based on current US grid averages. For a typical house, switching from standard air conditioning to a well-designed solar chimney can keep nearly 17,900 kilograms of carbon dioxide out of the air each year, about as much as parking a dozen cars for the same period. The dual season advantage is real, too. That same chimney can help ventilate in summer and boost passive heating in winter, stretching every dollar spent. With a build cost as low as $300, the break-even point comes quickly, especially when rising energy prices and future carbon penalties are factored in. For homeowners weighing the next step, the numbers make a clear argument. This is more than a gadget. It is a payback machine. The next phase is all about turning that logic into action, one build at a time. A solar chimney that cools an entire house doesn't require rare parts or a specialist toolbox. Every component is available at a local hardware store, and the total bill stays under $300. The main structure uses 2x4 lumber. Standard 8-foot lengths form the frame. For the shaft walls, exterior-grade plywood does the job. A single 4x8-foot sheet covers most builds. Plywood is inexpensive and widely available. The sun-facing side needs a black metal plate, either steel or aluminum, about 1 millimeter thick and 1 square meter in area. This absorbs solar heat and drives the airflow. A clear, ultraviolet stabilized polycarbonate sheet, 4 millimeters thick, covers the shaft's upper opening to let in sunlight while blocking rain. 2 adjustable dampers, each an 18-inch square, control the flow at the inlet and outlet. Dampers let you balance intake and exhaust. For those adding evaporative cooling, a basic submersible pond pump, 12-volt direct current, rated at around 100 gallons per hour, circulates water over a shallow tray at the base. Evaporative cooling is optional but effective in dry climates. A simple digital hygrometer or temperature logger, usually under $20, tracks performance. A hygrometer helps you measure humidity and temperature changes. Optional, a 10-foot length of half-inch PVC pipe can serve as an earth tube, pre-cooling incoming air using the steady ground temperature found 4 feet below the surface in many dry U.S. regions. Optional earth tubing can improve performance in very hot climates. None of these materials are specialty items. Plywood, lumber, metal sheet, polycarbonate, dampers, pipe, and a small pump, each is a commodity with prices that rarely fluctuate beyond a few dollars. Even with regional cost swings, a careful buyer can source all parts for less than $300. A careful shopper can keep costs low. With the shopping list in hand, the next step is construction, assembling these pieces into a working system that delivers measurable cooling. Every successful solar chimney build follows a clear, 8-step sequence. The process begins with site selection. Pick a south-facing wall or roof section that gets full sun for most of the day and offers at least 6 feet of clearance from trees or other structures. Next, frame the shaft using standard 2x4 lumber. Cut and assemble the studs and cross pieces into a rectangular box about 8 to 10 feet tall, then sheath the sides with exterior-grade plywood for strength and weather resistance. Step 3 is installing the absorber plate. Attach a black painted steel or aluminum sheet to the sun-facing interior wall of the shaft, making sure the surface is tight against the plywood to maximize heat transfer. Seal all edges with high-temperature caulk to keep out moisture. Step 4. Add the glazing. Fit a sheet of UV-stabilized polycarbonate over the top opening of the shaft, securing it with weather-resistant screws and sealing gaps with tape or gasket material to prevent leaks. Now mount 2 adjustable dampers, one at the base to control air intake, and one at the top to regulate exhaust flow. If you are adding the optional earth tube, Bury a 10-foot length of half-inch PVC pipe at least 4 feet underground, then connect it to the shaft's lower inlet. For evaporative cooling, set a shallow tray at the base and connect a small submersible pump to circulate water across the surface. Finally, use a digital hygrometer or temperature logger to monitor performance and fine-tune the damper settings. With the build complete, the next step is commissioning, verifying that your system delivers real cooling and airflow. Commissioning a solar chimney means proving, with numbers, that the system delivers real cooling and safe operation. The first step is thermometer logging. Place a digital temperature logger at both the inlet and the outlet. Over several sunny days, record the difference. The goal is clear: a drop of at least 8 degrees Celsius, or about 14 degrees Fahrenheit, between outdoor and indoor air. This is the same performance documented in Yazd's IoT sensor campaign and matches the upper end of what peer-reviewed studies report for well-built passive shafts. Next comes the permit. Most US cities and counties treat a solar chimney as a ventilation accessory. The typical building permit fee ranges from $50 to $150. Inspectors may ask for basic documentation, shaft height, material fire rating, and a wiring diagram if you are adding an electric pump for evaporative cooling. If a pump is installed, it must be plugged into a GFCI protected outlet, following National Electrical Code standards. This protects against electrical faults, especially in outdoor or damp conditions. Maintenance is straightforward. Check the dampers for smooth movement every season, clean dust from the absorber plate once a year, and inspect the polycarbonate glazing for cracks or yellowing. If you are running a pump, plan to replace it every 5 years. Painted plywood may need touch-ups after 10 years, while the metal plate and polycarbonate glazing can last much longer with minimal care. With these steps, any homeowner can validate performance, satisfy code requirements, and ensure long-term reliability. A system that passes these checks earns its place as a credible, do-it-yourself solution, grounded in physics and ready for real-world use. The next question is how this approach stacks up against the cost, energy use, and emissions of conventional air conditioning. The physics haven't changed in 3,000 years. Only the incentives have. Now you know both. As energy prices rise and summers break records, the future of comfort is hands-on, not plug-in. Subscribe for more practical solutions you can build yourself.